Hello everyone. Today we start a new topic. We are going to study the Monte Carlo methods and how powerful they are, especially when it comes to solve problems in Bayesian inference. So remember from our previous tutorial, when we use the Bayesian approach to solve a machine learning problem in general, we end up computing the posterior predictive, and the posterior predictive is the integral of the prediction but over all the possible parameters values, right? And that's why we integrate that times the posterior. Turns out that in general, this integral cannot be solved analytically as we did in the Bayesian linear regression setup. For example, this could be a neural network or any other complex model in where we don't have a closed form for the expression of the prediction, right? So in this case, that integral is not going to be easy to solve. The good news is that we can find a very good approximation of this by doing just one thing, taking samples from the posterior distribution of the parameters. So let's get familiar with the notation. In general, we will see across different books or websites that this integral is the expectation of a function under the posterior distribution. So we can see this notation or that notation. Phi in this case is going to be any function that we use to predict or to perform any inference times a probability that usually goes over the domain of the parameters of phi. And we will see this brackets notation to refer to the expectation of this function under this distribution. So this is the same, that is the same. So f or phi are both used in several cases, and the posterior or any probability of x are the same thing. So let's use this notation. With Monte Carlo methods, what we are trying to do is to solve two things: generate samples from any given distribution or estimate expectations of functions under this distribution. The second point is this integral. So again, the function phi is going to make inference or a prediction that depends on the parameters x, and there is a distribution which is our beliefs about the function parameters. And again, this is the same we saw in our Bayesian inference setup, right? P of x could be our posterior of the parameters w, and phi could be our prediction function that depends on those parameters. So as you can see here, all the time we apply the Bayesian method to solve any problem and we try to compute the posterior predictive, we end up in an expected value of a function, the expectation of the prediction under the posterior distribution. So this is why Monte Carlo methods are powerful, because they help us a lot when it comes to solve problems by using the Bayesian approach and, in other words, taking into account the uncertainty of the model. So we will see that generating samples from a given distribution is what solves everything. Why? Because if we are able to generate samples from P of x in this case, then we can estimate this whole integral or the expected value of the function phi by calculating the average of phi applied to our samples, as you can see here. So if we get samples from P, we just need to apply phi to every single sample, then add them up and divide by the number of samples, just by taking the average. In other words, it's kind of the same what we do with an integral over a distribution, right? When in general, when we calculate the integral of something, but we multiply by the probability of our integral domain, what we are doing is calculating a weighted average. With this estimation, we are assuming that the way we sample from P is somehow capturing those weights by getting more frequent samples in the areas where P is bigger. So in that way, we end up weighting more in this average. So that's why we can estimate this expected value by using this approximation. So as a summary, again, what we want to calculate, for example, is the integral of a prediction times the posterior. Whenever we need to solve these kind of problems, the first thing we must do is to see if we can take samples from that posterior distributions. Let's say we get R samples of theta in this case, and then we apply our prediction for each of the samples and just average them. With that, we end up estimating the whole integral with that average. So for example, let's say we have a Dirichlet distribution. Remember from our previous tutorial, we learned what is the Dirichlet distribution. In this case, we have a two simplex in where every single point in the simplex has three numbers and they add up to 1. They are greater or equal to 0. And let's say that we have the posterior of our parameters represented with a Dirichlet distribution. Okay, let's say we have three parameters and our posterior of those parameters here. So this indicates that the concentration of mass is mostly here. So if we want to solve the expectation of a function with this posterior, the first thing we need to do is to get samples from this distribution. Let's say most of the samples are going to concentrate here. And after we get the samples, we grab all of them and we make the predictions of our model for each of the samples, right? We're going to have a prediction that is going to be different on every case because we will have a different vector of 3 theta values, right? And after we make all these R predictions, we grab them and average them. With Monte Carlo simulations, we can even estimate pi, for example. Imagine we are capable of generating random samples that fall inside a square, as you can see from the animation there, right? Imagine that we have a fully random way to generate uniformly samples inside the square. So after this process finishes, after we get enough samples, the more samples we can get, the better. We can do the following to estimate pi. Let's say that we only grab the points that fall inside the circle of radius r. Note here that the side of the square is 2 times r, right? Since we know that the area of the circle is pi times r squared, and the area of the square is 4 times r squared, if we divide both, we obtain pi divided by 4. So pi can be calculated as 4 times the area of the circle divided by the area of the square. That division can be estimated by counting the number of red dots divided by the total number of points. So the more points we have, this relationship between both areas can be represented as just 2 numbers by counting the number of points that fell inside the circle versus all the random points. So if we have a very accurate way to generate random samples and we have enough resources to generate many of them, we can estimate pi. Okay, so back to our expectation. Remember that this is the sequence of steps we must do in order to solve the expected value of our inference model or prediction, given that we have the posterior. As you can see, everything gets centered in this thing. The core of the solution is going to be our capability of generating R samples from the posterior distribution. The problem is that generating samples from a distribution in general is very hard, unless it's a very simple distribution. So our assumption from now on is going to be that we are able to generate random numbers from a uniform distribution. As you know, those are pseudo-random numbers because there's no way to generate fully random numbers without a physical process. And we just use pseudo-random numbers from the computer. That's a whole another area of research. But for now, let's assume that we can generate random uniform numbers. So let's start with a simple and very useful distribution, the Gaussian distribution. The idea is that we are going to be able to generate uniform numbers and then use somehow a transformation that will map those uniform numbers into Gaussian numbers. So the first trick that we will study is the trick that uses the CDF, or cumulative density function, of a given distribution. Okay, let's remember the CDF. Okay, we all know the PDFs, which is the probability density function, and we are all familiar with the normal distribution. In this case, we are seeing a normal histogram, right? So let's try to understand what the CDF is. If we start walking from left to right, trying to grab a more and more portion of the mass of the normal distribution, then we will see this effect. Let's say we start working from left to right and we start painting in orange the points that we already have. If we keep moving to the right, we will end up grabbing at some point 100% of the mass. So the CDF is a plot that indicates how much mass we have captured from our walk. So we start from the left. You can see the histogram up there in the image. So we start walking. If we already grab that piece of orange mass, then it means that we are a bit higher in our CDF plot. We continue walking. We roughly captured 50% of the total mass there. So we are kind of like in the middle. means that we are close to 0.5 here. This indicates the percentage of mass that we have captured. If we continue working to the right, we capture more than 80% already of the mass, and at some point we will capture almost 100% of the mass, and that's where the CDF gets stable at 1. This is an image that combines both plots together. This is the CDF of the normal and the PDF. So why the CDF is useful is because it allows us to travel from a 0-1 range uniformly. Let's say, imagine that we randomly choose one point uniformly in this range from 0 to 1, let's say that point. Then with the CDF, we can use the inverse and travel from this point to the corresponding Gaussian point. So let's analyze this image. Here, again, we have the CDF and the PDF, but now we have these blocks indicating different areas of mass. As you can see in the normal distribution, most of the mass is concentrated here in the middle range, right? In the blue and pink ranges. If we look at the CDF, the same thing happens. The blue and the pink areas are also grabbing most of the portion of the curve. And why? Because in that area, our CDF has a higher slope. So since the slope here is higher, whenever we choose a uniform number in this range, the areas of higher chances to get the number are going to be the same areas of higher chances to get Gaussian numbers. So this is why the shape of the CDF is somehow capturing the shape of the normal distribution, just in a different space. But the good thing here is that for us it's very simple to sample a random number from 0 to 1 and then transform it into a Gaussian number. But we couldn't do that here, because if we start sampling random numbers in the domain of the PDF, we would get just a uniform distribution, not a Gaussian distribution. The only way to get a Gaussian distribution is to somehow guarantee that we are getting more points in the zones of bigger mass. And what is allowing to do that? The CDF, because the CDF is actually grabbing a bigger portion of the uniform range in the same way the Gaussian distribution grabs a bigger portion in this range. So I tried to give you many insights for you to understand or feel how this works. I hope you could get it from these images. But that's why the trick of using the CDF to get samples of a distribution actually works in practice. Again, so what we use from the CDF is the inverse of the function, right? Because we need to travel from a uniform point in the 0-1 range by using the inverse to find the source point that actually has the distribution or the corresponding PDF of this CDF. But guess what? In general, in practice, we don't have access to the CDF. We will see later methods to deal with that. At least with the Gaussian distribution, we do have it, right? But in other more complex scenarios, we won't have access to the CDF. Another very easy distribution to get samples from is the multinomial distribution. As you know, the multinomial distribution is a categorical distribution that gives us a proportion as the probability of falling into one of the k possible categories, right? So let's say we have this distribution for 5 possible categories in a multinomial with these probabilities. And we want to generate samples from this distribution. How we do that is very easy. We just need to generate random uniform numbers between 1 and 100 and then check where that number falls. So we need to create buckets of the size of the probabilities given by this multinomial distribution. So at the end, bigger buckets will have higher chances of getting the random number inside them. So that's why at the end, if we generate uniformly numbers here, let's say that we generate b equals to 50, since 50 falls in the third bucket, then our sample is going to be the number 3 or third category. Pause the video and make sure you understand this. At the end, having buckets of the size of the probability guarantees that we are maintaining the same distribution when it comes to the generation of the samples of the categories, because higher probabilities get higher buckets, get more numbers when we sample from the uniform distribution. Let's see another very known trick called the Box-Müller trick to generate samples from a Gaussian distribution. Again, here what we do is to generate samples from the uniform and then we transform them. We will do kind of like the same thing we did with the CDF, but now it's more complex. So please bear with me till the end, because if you understand this, you will have done a big progress. First intuition is that if we integrate the 3D Gaussian PDF, hold the cross domain, in this case we have a source domain of two variables, let's say x and y here, and the height is an indicator of the probability. So this could be the PDF. If we calculate the integral in these two variables across the whole possible domain, we will get 1 because it's a density, right? Okay, so let's use the same intuition or idea we use with the CDF. Let's say that we can walk from left to right and start grabbing a bigger portion of the PDF until we complete 100% of the mass. So if we manage to be able to choose randomly one number from this range, let's say we find one number R somewhere in the middle of this process, and we can travel back to the source points that generated that proportion of mass, then we will find those Gaussian source points as our Gaussian samples. This is the first intuition. So it's kind of similar to what we did with the CDF, but now in more dimensions. But how we travel from one resulting integral value to the source xy points. Okay, this is the integral in the two variables of this PDF. These two terms or factors are the PDF of the Gaussian in one dimension in x and then in y. We can do that here because we are assuming a standard Gaussian in where variables x and y are independent, right? There's no correlation for this very standard distribution. So we can multiply both PDFs and it's going to be equal to P of x and y here, right? So you can check that by using the Gaussian PDF, we get this equation. Also, of course, we are assuming that the mean is 0. So this is why we get this term. If we integrate again the PDF across all the domain of x and y, then we will get 1 because this is a density. If we look at the 2D plane in the x and y domain here, and we make a horizontal plane cut to our PDF, we get a circle. So every single point that lives in this circle will follow the circle equation, right? Let's say that if the circle has radius r, then this is going to be the equation for every single point living in this curve. So the idea is to see how we travel from the resulting integral value to the x and y domain. This is one quick arrangement we can do in the equation, just putting together these two, and we can take out of the double integral this 1 divided by 2 times pi here. The first thing we need to do to simplify this is instead of depending on two numbers, we can make this to depend on just one number. Because the idea is that the volume captured with this double integral ends up in some function of one value, such that later, if we sample uniformly from that value in a given range, 0, 1, then we can travel, assuming that that's the result of the volume, we can travel back to the source points. I know this might sound complicated now, but please bear with me here. So again, what we are trying to do here is to find sort of a CDF of this 3D density. For that, we need to find a volume function whose scope is just one number, the resulting mass. We know that we are getting there because we are calculating now the double integral across the whole domain, and we know it's 1. The idea is that we can calculate this integral to some certain point in the domain to get an intermediate volume. So later, if we find that function, then we will sample from that resulting intermediate volume uniformly, and using the function, the inverse of it, we will travel back to the source points. So let's make this equation better. The first thing we're gonna do is to move from x and y space to the polar coordinates, meaning that instead of dealing with x and y in the circle, we will deal with r and theta. Probably you've seen this from Calculus 101, that this is the way we transform coordinates. So visually you can see that when we have points in this circle, now we will have the same points, exactly the same thing, but instead of defining them by x and y, they will be defined by r and the opening angle here. It's just another way to refer to the same points. And these are the two equations that we use for that transformation. So if you're not so familiar with this change of variable, please pause the video and make sure that you understand this very well. Okay, so applying those equations, we end up in this integral. You will see why this integral is going to look simpler very soon. We just replace x and y by using our previous two equations. Okay, we can simplify this integral a little bit. We can notice here that theta does not depend on this integral that goes in the domain of the radius, only depends on the integral that goes in the domains of the angle between 0 and 2 pi. So we can take that out of this first integral, and then here we are integrating from 0 to 2 pi the angle. In other words, we are adding up one full round of opening of the angle, and the result of that is 2 pi. It's basically sum the angle across all the possible domain in one round. This is 2 pi. And this can be divided by this term here, so it's going to be simplified. So now our integral looks easier. Okay, we need to make just one more variable change. We can simplify this equation further by replacing r squared divided by 2 by a new variable called u. So if we do that from calculus, remember that whenever we use a new variable, we needed to calculate the derivative of this new variable with respect to the previous one. So if we calculate the derivative of u, we're going to have 2 times r divided by 2 times dr. So these two terms can be simplified. So now if we replace this here, we're going to have e to the minus u, and this r, the r, are going to be replaced by du. So we will end up in this equation. So now it looks simpler. And note that we keep the same range here, because whenever r goes to infinity, r squared divided by 2, which is u, also goes to infinity. So this is why we maintain the same domain here in the integral. So now we are building the function I told you before. The idea is to build a function that somehow left variable the amount of mass that we are capturing in the integral, such that later we sample from that variable number and travel back to the source points in the circle. That's the idea, because we know that those points are Gaussian. So one way to do this, we know that at the end the mass of this integral will no longer be 1 if we start limiting the limit here. Instead of going to infinity, we will go to a variable number. So let's start seeing what happens if we use r squared divided by 2 here instead of infinity. We will see that if r squared divided by 2 goes to infinity, we will have 1, and if this term is 0, we will have 0. So here we have a function that goes to the range between 0 and 1 as we want, and depends on the value of r. So let's calculate this integral. Actually, we can solve it, right? We know that from basic calculus that the integral of e to something is exactly the same, but now we need to multiply by minus 1, and we need to evaluate on the limits of our integral, which are these limits. So this is the way we do that. This is going to be 1, so we end up in this result. So finally we have our function. Why? Because our function goes between 0 and 1, and if we use numbers in the middle here, we end up in masses that are between 0 and 1. It's like the CDF method. And we are going to need to use f to the minus 1 to find these source points that led us to the mass that we obtained from this integral. So the idea is to isolate r, right? So let's say that p, which is f, we know that f goes between 0 and 1, so we can use any p to represent this function, and we know that p goes between 0 and 1, and this is going to be our uniform number actually, but we need the inverse of this to find the respective r. So we just isolate r by subtracting 1 here and then applying the logarithm here. We end up in this thing. So r is going to be this equation related to p. Actually 1 minus p is just another random number between 0 and 1. So we can simplify it by using s that goes between 0 and 1. So again, finally what we do, we just generate one uniform number s between 0 and 1, and with this equation we can obtain r. And we know that r is actually the amount of mass that we are capturing in our 2D PDF. So then, by using our previous polar coordinate equations, we can go from r to x and y, which is our original domain numbers. And we know that those numbers are Gaussian. You can see here that we introduced another number, t, that multiplies 2 pi y, because at the end we need to allow this equation to be somewhere in the middle between 0 and 2 pi. We have one dimension here, just s, but we have two dimensions in our circle. It's not just the radius, it's also the angle. So with S, we find our R, but now with T, we find the angle. And by using these two uniform numbers, we can somehow modulate the angle and the radius. So finally, to generate two Gaussian numbers, we must generate two uniform numbers between 0 and 1 and then apply these two transformations. And that's it. To apply the method is super simple, but to understand it is very complex. Now we just need to add one more thing, which is how to sample from a Gaussian that has any mean and any variance, right? Before, those numbers were for a standard Gaussian, mean 0 and variance equal to 1. Now we just need to shift and scale. So if we want a Gaussian with parameters mu and sigma square, we just need to add mu here to shift our number x, and we need to multiply this term by sigma. So with these two equations, we can very quickly generate any amount of random Gaussian numbers coming from uniform numbers s and t.